Welcome back. I hope we are all refreshed. I certainly am. And I hope you are ready to go on with chemical equilibrium. In the first session, we worked up to a point where we looked at the definition of chemical equilibrium. What we're going to do now is we're going to build on that definition of chemical equilibrium, and we will start to show some graphs with that chemical equilibrium so that we can start to understand and to see, while a system is building up to equilibrium, the rates that we will look at, as well as at the end we will look at the concentration. How does the concentration change as we build up to chemical equilibrium? In front of us is an example of a reversible reaction. Remember what we said, what is a reversible reaction? A reaction where the reactants convert into product, and when there is enough product, the product will convert into reactant, but that process happens at the same time. We actually use the word simultaneously. So when we look at the production of ammonia by using nitrogen and hydrogen, in front of us we have a balanced reaction. It is very important that the reaction is balanced. Now, if we break up this reversible reaction into firstly the forward and secondly the reverse reaction, we firstly can say the reaction that we read from left to right is the forward reaction. So the forward reaction, if we only write down the forward reaction, we will not be using the double arrow. We will only use an arrow pointing in the direction of the formation of the product. So back to hydrogen and nitrogen reacting to form ammonia. That is read from left to right, and our arrow will be to the right. When we write the reverse reaction of what happens here, we can write it the same, but we need to remember that it will now change. We change the arrow to the opposite side. Why? Because when we look at the reversible reaction, what was the product now becomes the reactant. And that reactant will now decompose, in this case, to form what was the reactant to be the product. I think I confused you now. Let me say the following. This is now for my reverse reaction, which is actually read from right to left. This is now my reactant. And my reactant is now, I show with my arrow, breaking up into the product of the reactants. On the forward reaction, these were the reactants. And this was my product of the reactants. Okay, just another note, that reverse reaction can also be written starting with our ammonia. So we can actually also write it as 2NH3, but what's now going to be very important is that we have an arrow showing forward, and we then show this is our products that's forming. So we must remember that the arrow must change when we write it in the opposite way. When we look at the forward reaction of this reverse reaction, make sure that you focus on the arrow there. You need to know that at the beginning, we have a high concentration of hydrogen gas and we have a high concentration of nitrogen gas. And the high concentration is due to the fact that it's the only thing that's currently in the vessel. So we have lots of nitrogen and lots of hydrogen. And because we have lots of hydrogen and lots of nitrogen, the reaction will actually be very fast. What about the ammonia? In the beginning, there is no ammonia, Therefore, there will be no reaction. Not just reaction, there will be no reverse reaction in the beginning. If I can go to a graph and plot a rate over time graph, I can actually do the following. Remember, we started off with a high concentration of nitrogen and hydrogen. So for the forward reaction, we had loads of this, and because we had loads of it, we had a high rate of reaction because there were lots of particles that could collide. And remember what we said, more collisions there is per unit time, the higher the likelihood of effective collisions, and that leads to a high rate of reaction. When we look at the reverse reaction, where the ammonia now convert back into nitrogen and hydrogen, remember at the beginning there is no reaction reverse, therefore we make our plot on the zero. After a while, now the reaction started. Remember, at first we had loads of nitrogen, loads of hydrogen, very fast reaction. There was no ammonia at the beginning, so we plotted the 2 points. Now, after a while, we will see that the hydrogen and the nitrogen concentration start to slightly decrease. And that happens because now the ammonia started to slightly increase. And when this slightly decreases, it starts to slow down. The reaction starts to slow down for the forward reaction. And while the reverse reaction is now getting more ammonia in the system, the reverse reaction starts to slightly increase. And this slight increase and slight decrease can be shown on the graph. Back at the graph, this was at the beginning, and this is now after a while. You can see that my forward reaction actually starts to slow down. And in that process, I have my reverse reaction where the concentration of the product, which is NH3, is now starting to increase, and the rate is also starting to increase. So we have more or less 2 plotting points after a while that will look like that on a rate time graph. Even a little bit later, remember we still have nitrogen, we still have hydrogen, but we also have ammonia now in the system. But the nitrogen and the nitrogen has become less and less over time, so it still decreases, but not at a high rate as before. So it decreases, but to a lesser extent. The ammonia still increases, but not like before. It also increases less per unit time. So even though this reaction starts to increase the rate, it's not as fast as before. So the forward reaction now actually slows down because of this decrease. And the reverse reaction increases slowly because of the increase of my ammonia concentration. That brings us to the graph. Now I want you to see what we've done on the graph now. I've now plotted the points over time. So I'm just going to explain again. What happened to the rate here is at the beginning we had loads of nitrogen and hydrogen that started to convert fast into our ammonia. At the beginning for the reverse reaction, there was no ammonia, but as soon as it started to convert and make ammonia, we had a reaction that looked like that. So if we would complete this, our rate of reaction graph will look more or less like that, and that is now for the overall reaction, where we look at the forward reaction and the reverse reaction. Then at the end, finally, our hydrogen and our nitrogen stops decreasing. Our ammonia stops increasing. So what happened here is, for both the forward and the reverse reaction, the concentrations of everything became or becomes constant. Not the same, the word is constant. So when we look at the overall reaction of the rate of the forward reaction and the rate of the reverse reaction, we can actually put it into a graph where the orange part will be our forward reaction and the reverse reaction is the blue graph, where we can see at this point from here onward, we actually have the rate of the forward reaction is equal to the rate of the reverse reaction. And that brings us to the next point, and that brings us to the actual definition of chemical equilibrium. Now, chemical equilibrium is a type of dynamic equilibrium when the rate of the forward reaction equals the rate of the reverse reaction. It must happen in a reversible reaction, and it will only happen in a closed system. So the rate of the forward reaction must be equal to the rate of the reverse reaction. A closed system, we know that the rate of the forward reaction is equal to the rate of the reverse reaction. Concentration of reactants and products that remain constant, these are all features of a chemical equilibrium. So if there's no closed system, there will not be a rate of a forward reaction that can become equal to the reverse reaction. So please make sure that you realize that chemical equilibrium can only happen in a closed system where the two reactions are at the same rate and the concentrations remain the same, constant. When we look at the concentration time graph for the same reaction, I want you to remember that I'm now looking at concentration. So the purple pink part will represent what happens to nitrogen over time. The yellow is what happens to hydrogen over time, and the red, the ammonia. So the concentration shows us that we start with high concentrations of nitrogen and hydrogen, and they will decrease over time in concentration, but we start with no concentration for ammonia at the beginning, and that will increase over time. Please make sure that you look at, when you get a graph, you must make sure, is it a rate graph or is it a concentration graph? Okay. Then at the point where we have horizontal lines, or let's say these horizontal lines are now parallel to the time axis, at this point all the concentrations of the reactants and the products remain constant. Remember, the word is constant. We do not say the concentrations are the same. Dynamic equilibrium. Remember when I gave you the definition of chemical equilibrium, I said it is one of the types of dynamic equilibrium. Now, dynamic equilibrium is established in a closed system when the forward and the reverse reactions happen at the same time, at the same rate. Same time means simultaneously. Both the forward and the reverse reaction continue. They do not stop. Even though it looks for us on a macroscopic view as if it stopped, for us it will look as if nothing is changing, but on a microscopic level, there's definitely still a reaction where the particles are still moving forward, reverse, forward, reverse. Examples of dynamic equilibrium is chemical equilibrium, as we've done just now. We also have phase equilibrium. Think of something that's in a closed container that's allowed to evaporate. and then saturated solution and precipitate, we also have a dynamic equilibrium in that system. And that brings us to the end of this session. Have a good one.